Hello and welcome to this WANDA webinar. First, I'd like to thank you for joining, and yeah, I'd like to get started now. We're going to talk today about modeling pipeline hydraulics in WANDA and on basic WANDA usage. If you have during the webinar you have a question, you can type it in the via chat or the question box, which you should be able to see. And my colleague Michiel Tucker is also available, and he will try to answer the questions during the webinar. At the end of the presentation, we also will take some time to answer the questions which are still left over. What I want to show you today is basic WANDA usage, and we're first going to have a quick look at the user interface. Then we'll build a simple model, and of course run some simulations with that model, view the results, then make it a little bit more complicated by adding the parameter script into it. And at the end, I want to show you the selection builder functionality, which is also included in WANDA. But let's start it by looking at the user interface. So if you start WANDA, then you get this screen. This is the diagram where you will be building your model. Here you can see the shape palette, where all the shapes like a pump and a valve are given, which you can use to build the model. And as you can see here, there are several tabs. So this is for WANDA Liquid, but we also have the heat module, so the heat components, but next to that we also have control components. And here on the right side, this is the diagram selection property window. If you have a component selected, then the properties of this component are shown in this window. That's just the basic user interface. And we start by building a model. We make it a very simple model, a gravity system, a tank which is on a hill with an elevation of 100 meters, a pipeline of 10 kilometers running down to an elevation of 0 meters. We're just going to put in the tank. This is a tank with an unlimited area, so it will always keep its head at the same level. Then we're going to add a pipe and the other tank reservoir on the bottom of the hill. We now have to connect the components. Just do that very easily by dragging these lines from the connection points. Basically, that's our model. Now, of course, we have to fill in some properties. So we're going to start here at the tank. Let's say that the water level of the tank is 2 meters above the ground level at that point. So, and since it is at 100 meters, we're going to put this at 102 meters. Next, we have to select a node. In the node, we also have to set the elevation of the node. So let's put that at 100 meters also. Next is the pipe. You can see already that there are some more input properties which you have to give. So first, you have to select what kind of cross-section it is. We're going to use a circle pipe. You have to put in the inner diameter. Now, let's say it's 500 millimeters. You have to select the friction model, and now we're going to use the Darcy-Weisbach model, and we're going to put in the wall roughness, so that's the K, and let's say it's 1 millimeter. For the dynamic friction, we're going to use quasi-steady. There are no additional losses, and we're just going to put in the length. And the length, as I said, was 10 kilometers, and I can put it in like this, so just put 10 and then the K and the M for kilometers, and if I press enter, see that the user interface automatically calculates this 2 meters, which is the unit I'm working in. I can also, for example, put it in like feet, and then it calculates feet. So this can be sometimes very handy if you have different units and you don't want to fuss about using the correct calculations factors to come to the units which you're calculating in. Let's go back to the kilometers. And here we again have to set the elevation. Let's say it's 0 meters. And this tank, the level is also 2 meters above ground level, so let's put it at 2 meters. So now I've put everything in. Now I only have to save the model. I have to go to a folder where I can save it, and I just call my case 1. So if it's saved, I can, in the model window, I can select Calculate Steady, or I can press Shift F9. And then it's calculating, and now it's finished. So if I now select the pipe, you can see also the outputs, the blue ones, are now filled. See, for example, there's certain discharge. You can also press on this button to get a graph. Now there's one thing to notice is that in the pipe I didn't give any information on the profile of the pipe. But based on the elevation of the H nodes, it determined the profile. So it just runs, zoom in here, from 100 meters at the bottom, 0 meters. The orange line is the headline, which runs just parallel to the profile. Of course, I can also have a look at the pressure along the pipeline, which is as expected because the profile and the head are running in parallel, is constant along the line. So this is, of course, you can easily use it to engineer your pipe. Of course, you also want to start running some transient simulations. And what we want to do is going to look at valve closure at the downstream end. So we need to go to add a valve to this model. So I select the valve, just put it somewhere into the model, and then I have to connect it. Now it's connected, but this doesn't look very nice, so I'm going to arrange it a little bit. And now I have to put some properties into the valve. So I have to select the type of valve. I'm going to use a standard characteristic, which is available in WANDA, and I'm going to use the butterfly valve. If you want, you can also, for example, use the KV characteristic if you have that available. For the diameter, I want it to be the same as the pipe. And I'm going to show you how you can easily copy this from the pipe. And for this example, it's a little bit simple, but you can imagine if you have more components, it can be very handy the next trick. So now I select, by holding the shift button, I select also the pipe. And you can see here all the yellow properties are properties which are in both selected components. So that's also, for example, the inner diameter. The white properties are only in the last selected component, which the red circle around it. As you can see, the diameter is in both. And what I can do now is go here up to this button, which is the copy to diagram selection. And if I press that button, then it copies the value from the pipe also to the valve. And as you can see now, it's no longer red, it became black, and that means that the property is the same for both components. So if I now select only the valve, you can see it copied the value, and that has now the same diameter as your pipe. So now basically the valve is added, but now I have to say that I want to run it in transient mode. So what I have to do then first is go to the model and the mode and options window and select transient mode, press OK. And now you can see here an action table has appeared, and I can say, okay, I want this action table. If I open it, here I can specify actions which happen in time. So at the beginning of my simulation, it's fully open. After 1 second, I keep it fully open. And then I will close it in, let's say, 50 seconds. Go to 0. Next thing which I have to add is, of course, some properties for the pipe. Because I want to do WANDA hammer calculations, I have to select the calculation mode WANDA hammer. Then I have to specify, of course, the wave speed, and you can do that in two ways. The first is physical, and then you have to put in the wall thickness and the Young's modulus. The second one is you specify it. And I'm going to specify it now, just for this example, on 1000 meters per second. So now everything is filled in. Then I can say calculate transient or press Alt F9. Oh, sorry, I will put that a little bit quick. Get here the message, you must have more than one time step to run unsteady. Yeah, that's true, I didn't specify how long it should run. So I have to go to the time parameter window. And I put here a time. I'm going to simulate for 100 seconds. We now go again to calculate transient. We have to wait a little. Now it's finished. So first have a look at the valve. Make a time series and graph of the discharge. You see at a certain moment it starts to drop rapidly till 0 when the valve is closed. So we are going to also include the valve position, and how you do that is just drag the graph into the other graph. What you can see now is that for the first 40 up to 40% open, about nothing is happening, but that's also expected for a butterfly valve. Above 40–30%, it's not doing much with the flow, and then in the last piece you can see it dropping rapidly. We also can of course make a graph of the pressure. You can see when the valve is closing, then the pressure rises, and then due to reflections it drops again. So we're just going to close this one. Now we're going to look at the pipe, and we're going to make some root graphs. We want to look at the head along the pipeline. So the red line, that's the maximum pressure. Orange line here at the bottom, that's the minimum pressure, and the blue line is the pressure at the present time step we're looking at. Now we're going to go to the time navigator. You get just a simple menu where you can just push forward. See, nothing is happening. The valve is closing, but it's not doing anything yet. And now, as you can see, the pressure starts to build up. The pressure wave going into the pipe, which reflects, comes back. The valve is closed, and you see it gives cavitation along the line. Now this is, since I only have 10 points along the line, this is a very rough calculation. I can make it a little bit less rough by changing the time step. I'm going to put it to 0.1 second, and then I'm going to press Alt F9 to run the simulation. So it's finished again. I'm going to speed up the movie a little bit, which you can do with this slider here. I'm going to play it. Again, at the beginning, nothing is happening. Now the pressure starts to build up. The valve is closed, and you get the reflection on the upstream boundary. Again, a reflection on the downstream boundary, which results in cavitation. And the collapse of the cavitation, you can see that gives all kind of pressure spikes along your line. Now you get already much more detail, because now we have not 10 points, but 100 points along the line. So the question is, of course, can I design a closure time of this valve which is in such a way that the cavitation does not occur? And of course what you can do is you can just modify the action table, rerun it by trial and error, but you can also do it a little bit more fancy. That's what I want to show you, is by using the parameter script. For that I have to modify first the model a little bit, because I cannot adjust the action table from the parameter script, so I'm going to use control for that. And I'm going to use the MSP component, which stands for multi-stage pattern, which is a control component which closes the valve based on a certain, if there's a certain trigger activated, it closes the valve according to a certain pattern. And I'm going to need a sensor. The sensor I connect to the valve, and it measures the valve position. This valve position I'm putting in its input signal. Zoom in. As you can see, there's two connections. One is for the input signal, which is the valve position, and the other one is a logical signal, which is a trigger, which I'm going to trigger by a logical tap. And as long as the trigger is not activated, to move it a little bit, the MSP component gives the input signal, just puts it to the output. But when it's activated, then the component starts to close according to the specified closure pattern. You can specify the number of stages. I'm going to work at this moment with one stage. You have first a freeze period. That's basically stating how long it should wait before it starts to move. So if I put that to 10 seconds, it waits 10 seconds before it starts to do anything. Then there is the ramp. And I'm going to, that's the speed at which it's closing. So I'm going to put that to 0.02, so it closes in 50 seconds. And it's going to, the endpoint is 0, so it goes completely closed. Now I also have to specify the logical signal, the trigger signal, to close. So it starts at 0, it starts at time 0 at 0. Then in 1 second it's still 0, and then after one time step after that it becomes 1. Just to ensure I did it correctly, I'm going to run the transient calculations again. And let's have a look at the valve position. And as you can see, the valve closes within 50 seconds as we want. So then the next step is getting the parameter script up and running. And for that you have to get an Excel sheet, which you can find in, if you go to your WANDA folder, there is a tools folder and there is a new parameter script Excel sheet. So I'm going to copy that. And it's open. Now you have to be ensured that macros are enabled, because there's a macro behind it which is used to create the parameter script file. And then I have to put here in the name some properties. So first I start with the numbering. I start with case 01. And I call that, the description I give it is closure speed 1. You don't have to put something in here, but it can be handy to do that, if you have a lot of cases, to sort them easily. I want to include this in the one. I'm going to say, call this one case 1. And here you have to specify your inputs which you want to chase. And you have to first to give a component name or keyword, or you can use general for some general properties. The general property I'm going to change is the simulation time, because if the closure time is going to be longer, I need to simulate longer. Next to that, to look at the MSP component, the name of the component is MSP space M1, so I have to type that in. Then I have to put the property I want to change. So I want to change the ramp 1. You have to be careful because it's case sensitive. So, and we're going to start with a simulation time of 100 seconds and a closure speed of 50 seconds. Of course, we want to do some more cases, so I'm going to put case 2 here. And this speed I'm going to put at 100 seconds. Then I have to simulate it a bit longer, so I'm going to put it at 200 seconds. So this is for my input. And of course I need also some outputs. So I'm going to the output sheet. First I have to specify if I want to save the child cases or not. Now I'm not interested in that, I just want to know the closure speed, so I'm not going to save them. And I'm interested in the pressure in this pipe. That's pipe P1. Can you just type that? Pipe P1. And then here I have to specify which property I want to look at. So that's the pressure. And then I have to specify if I want the min or the max. So I'm going to start with the min. But of course, the maximum pressure is also important. So I'm also going to put that one in. So now I'm finished, and I can just press here the Create WPS button. Then I have to select the mono case, which I want to use. Now I'm more directly in the proper folder, so I can select case 1, say save. Now there's a question, do I want to save this location? Yes. And then the WPS file is created successfully, so I can just press OK. Then I'm going back to WANDA, to the model menu, and here at the bottom there's the run parameter script. I'm going to press that button, see if it's running. Yeah, it's running. And then we have to wait till all simulations are finished. And it's finished. And then you get this Excel is opened with the outputs, and then here we can see the inputs which I've given in here, the extreme pressures. And for example, you can see that for the 50 seconds closure time, the pressure is higher than for the 100 second, that as expected. But still in both cases we see cavitation occurring. So what you then have to do, of course, is just take the next step, and then is increase the closure time. So we have to put in an additional line. I don't have to calculate these two anymore. So I'm going to put it at 300 seconds. And we are just doubling the closure time. Put it to 200 seconds. Then create the case and run it. No, the valve is now closed, it's almost finished. Get the results, let's see. Now there's no cavitation, and so this pressure is much lower. But maybe if you have 150 seconds, it would be even better. It would be also okay. And then the faster closure time might be more acceptable. So basically what you want to do is optimize this closure time. And of course you can do that with the parameter script. It makes it already more easy to do this. But you can think, if you have 10 valves which close, 10 different tap-offs where you have to deliver water, then it becomes already more complicated. And for that we are looking now at the moment if it's possible to implement optimization routines into WANDA so that you can automatically optimize the closure pattern or the search channel volume. And that's something we want to develop in 2014. And of course we will keep you posted on this development, but it's probably good to know. So let us jump back to PowerPoint presentation. So we have had a quick introduction of the user interface. We have created a simple model. We have run some simulations and viewed the results, and at the end I showed you the parameter script. So now we are at the last point, and it's the selection builder functionality. I want to show that with the network example case. This case you have all available already in your version of WANDA if you have WANDA. If you go to the open example, you can choose between the heat, liquid, or the parameter script. The parameter script, there's an example of the parameter script, and in the liquid, several liquid components, liquid examples, and one of them is the network case. This represents a drinking water network. We have here a supplying pumping station. So you have several locations where water is supplied to. And of course the question is, what is the maximum pressure occurring in this system? And you can start by clicking around the model and looking, okay, this one is lower, but of course it can be much more easy to do that, and that's by selections, and we can here select all the pipes. So you have to think a little bit about it, but now we've selected all pipes. What we can do then is go to the pressure, ensure that the extreme values are shown, and then press here the button to create a spreadsheet. Now it's only giving the pressure range, but what we can do is select here the min and max separated. Make a separate column for the minimum and maximum. And the final step is, of course, sort by the pressure. And now I can easily see that in this pipe cavitation is occurring. So what I also can do is, if you have a bigger model, is select the component, and then press F4, and then you zoom in on the selected component. That makes it easy to find the selected component. And if you have no component selected and you then press F4, then you go back to the entire model view. So with this option you can easily find which component, where is the minimum pressure occurring. What you also can do is start using the selection builder. If I press this button, I get a selection on keywords. For drop down list of the keywords which are available, I'm going to select the loop and say select. And then I'm going to create a root graph of the head. You see, if you save this and maybe use the parameter script, you can easily look at this graph because you can just open it via the selection builder. You can have a look. Now here's the pumping station and you see the pressure wave running in. There are some reflections due to the other branches. Since these two are connected because it's a loop, pressure wave enters here and then at this point the pressure wave meets and you get cavitation and it implodes. That sends a lot of pressure waves into the system. What you also can do is start selecting on the pressure. And then I'm going to select on the minimum pressure occurring. So let's say select all components where the minimum pressure is lower than 1 bar. That's almost everything. What I can do then is then give them a nice color. I'm going to color them green. And then deselect everything and say, okay, now I'm going to go a little bit lower to have a bar. That are already less components. And I'm going to make them yellow. And of course you probably feel it coming now. So I'm going to 0 bar, below 0 bar, select some components and then I'm going to give them orange. And the final is below half a bar. First deselect everything. So, and now in a glance you can see, okay, in this piece that's not going to happen, something is going to happen. You have an overview of how the pressures are divided along your network. Makes it relatively easy to see and make it visual, the results. So the last thing I want to show you is, for example, you have done this study, you have done all the calculations, and then the flow rate of all the taps have to be increased by a factor of, let's say, 1.5. It's maybe a little bit big, but let's assume that. How you can easily do that is if you go to the type, and you select here in the drop-down list the tap with non-return flow and the tap with return flow. So now I've selected all the taps. I'm going to the initial delivery rate. What I'm going to do is I make a spreadsheet again out of it. I select entire table and then I'm going to press this button, which is an operation with selection. So I can add something, I can subtract, divide, or in this case I want to multiply it Press OK, and then you see everything is multiplied by 1.5. So I already went this case for you, which is in here. Of course, then I can open here also the selection builder and create a graph of the loop. And if I do it together with this other case, then press Ctrl T to get Time Navigator, closing this one. You see it's printing in both. You can easily compare the results from both. And this is the one with the higher flow rate, and then you see the pressure is a little bit less than in this case. And then one thing I want to show you, of course, because you also want to know how you can add this keyword to a route. And that's relatively easy to do. You have to select the route. You select the first pipe, and then you hold the Ctrl and the Shift button, and then you select. Now let's say I'm going to pick this pipe in the. And then it automatically creates a route between the 2 points. Sometimes you have to make it in smaller steps to get the route you want. And then you can here in the selection, you can add keyword to selection. So I'm going to do this, call it test routes 10 or something like that. See, it automatically adds this keyword, and then I can also select this route and also create the graph along this route. So, now, as I showed you, you can easily make selections and you can easily get them back. And also these keywords you can also use in the parameter script if you want to change a lot of components, or you want to know the pressure of all pipes, for example, and not interested in only one pipe. So that was what I wanted to show you about viewing results and using the selection builder functionality. I hope it was very useful for you. I want also to point out that on the 17th of October, we plan our next webinar. Of course, you will get an email from that. It will be on the system characteristics functionality and the pump energy module. And I also want to remind you, if you have heard already, on the Delft Software Days, which run from the 28th of October till the 8th of November. And there's a WANDA basic course on 5 and 6 November, and also a WANDA advanced course on 7 and 8 November. And you can find more information on the website, delftsoftwaredays.nl. I'm going to now have a quick look if there are any questions left, and we come back to that to answer that. And I want to ask you if you can take some time to fill in our polls, which I'm going to start right now. Okay, I've looked at questions, but there are no questions left. I think everything is answered. I'd like to thank you for your attention and for attending this webinar, and I hope to meet you again in another webinar or maybe on the Delft Software Days. Again, thank you for your attention.